This is Dr. Shankaraiah from Department of Physics. In today's presentation, I am going to discuss a topic from Module 4, which is magnetic and superconducting materials. So today's topic is applications of superconductors. So I've discussed in earlier presentation what is superconductors and what are the properties of superconductors, classification of superconductors, and BCS theory, which is a quantum theory that explains why we have zero resistivity in superconductors. Okay, so in this presentation we will discuss about applications where these superconductors are being used. Okay, so utilization of superconductivity in practical applications is severely limited by the very low temperatures required to maintain the superconducting material in the superconducting state. Okay, so if we want to use this superconducting material in practical applications, we have to maintain the temperatures to be very low. Only then we can maintain the superconducting state of these materials. So that is the first limitation, right? We need to maintain the temperatures very low so that we can use the superconductors in practical applications. So the first application is power transmission. Okay. If the national grid were made of superconductors rather than aluminium, then the savings would be enormous. So right now we are using in power transmission we are using aluminium material. So if we can replace this aluminum material by superconductors, then we can save lot of power. Okay, so the savings will be enormous. There would be no need to transform the electricity to higher voltage. This lowers the current, which reduces the energy loss to heat. Okay, so because we know that superconductors, once we induce current in a superconducting ring, this current will flow forever. So that is why this is called as, so this current will be flowing in the superconducting ring for 1 lakh years. Okay, so that is why if we replace this aluminum material by a superconducting material, we can save lot of money. So in power transmission. So first application of superconductors is power transmission. We can use these superconductors in power transmission. And the second applications of superconductors is transformer and electrical machines. So we can use these superconductors as in transformers and electrical machines. Superconducting coils in transformer and electrical machines generate much stronger magnetic fields than magnetic circuits employing ferromagnetic materials. If to make the transformers, if we use ferromagnetic materials, they are going to produce very less magnetic fields rather than the superconducting material. So if we use superconducting material, superconducting coils in transformers and electrical machines, which generate strong magnetic fields. So these superconductors can generate strong magnetic fields. If we use ferromagnetic materials, they will generate not very strong magnetic fields, low magnetic fields. So normal eddy current losses and hysteresis losses will not be present in superconducting devices, and hence the size of the motors and generators will be drastically reduced. Very important. Whatever electrical machines or transformers we have right now, if we can use superconducting materials in making transformers and electrical machines, the normal eddy current losses and hysteresis losses will be very less if we use superconducting materials in making transformers and electrical machines. And hence the size of the motors and generators will be very less. The size will be reduced if we use superconducting materials in transformers as well as electrical machines. The superconductors are likely to revolutionize the whole range of rotating electrical machines, making them smaller, lighter and highly efficient. So if we can use these superconducting materials in making transformers and electrical machines, then they are going to revolutionize these machines and generators. If we use superconducting materials to manufacture transformers and electrical machines, these superconducting materials are going to revolutionize the whole range of electrical machines, making them smaller, lighter and very efficient. Okay, so this is the second application of superconductors, which is transformers and electrical machines. If we can use superconducting materials instead of aluminum or other materials, ferromagnetic materials, we can make the transformers and electrical machines smaller in size and lighter in weight, and still they are very efficient. For example, a superconducting generator about half the size of a copper wire is about 99% efficient. Typical generators would be around 50% efficient. Okay. So if we can use superconducting material in making up in manufacturing a generator, then the generator size will be half the size of the generator which is manufactured using some other material like copper wires. Okay. So, and even though the size of the superconducting generator is half of the size of the copper wire generator, the efficiency will be around 99%. So, if we use a superconducting material in manufacturing a generator, size will be reduced by half, and the efficient will be also doubled, almost 50%, and it is 99%. So, efficiency will be doubled and size will be reduced by half. Okay, so that is the advantage of using superconducting materials in manufacturing generators, motors, and electrical machines. So the third application of superconductors is research and diagnostic equipments in medicine. Okay, so we can use superconducting materials in research as well as diagnostic equipments in medicine. We can use in research as well as in medicines. Okay, so how high magnetic fields are required in many areas of research and diagnostic equipment in medicine. So what we are saying is that in carrying out research, sometimes we may need to apply high magnetic field to study a property of a material. Okay, so we can generate high magnetic fields by using superconducting materials. Similarly, high magnetic fields are also required in diagnostic equipments in medicine. Okay, so wherever we need to generate high magnetic fields, we can use this superconducting material both in research as well as in medicine. So the electromagnets are cumbersome, being very big, demand large electrical power, require continuous cooling. If we use electromagnets to generate high magnetic fields, they are very big. The electromagnetics can generate magnetic field, but they are very big and they require more electrical power and continuous cooling. So this is the disadvantage. And if we use electromagnets to generate high magnetic fields, in the place of electromagnets, if we use the superconducting materials, they will generate high magnetic fields and they are small in size and light in weight and still more efficient. So that is the advantage of using superconductors in research as well as medicine. Superconducting solenoids produce very strong magnetic fields. So superconducting solenoids produce very strong magnetic field. They are small in size, less cumbersome, and they do not need neither large power supplies or means of removing heat. So if we can use superconducting materials in making solenoids, then these superconducting solenoids can produce very strong magnetic fields which are required in both research as well as in medicine. Okay, so if we use superconducting materials in making solenoid, they are small in size and less cumbersome. Okay, if we use superconducting materials in making solenoids which can produce strong magnetic field, they also do not need more power supplies. We don't need any power supply, and when we do not need it to supply any power, then there is no heat. So when there is no heat, then we can save lot of power. So the only power required is to bring the solenoid into the superconducting state and maintain it in that state. Okay, so only one thing which we need to do is that we need to bring the solenoid, superconducting solenoid. This solenoid is a superconducting solenoid. We need to bring the superconducting solenoid into the superconducting state, and we need to maintain this material in that superconducting state so that it can generate very strong magnetic field which we require in research as well as in medicine. The the low power requirement and simple cooling technique leads to a large saving in cost. Okay, so because the superconducting solenoids do not require large power supplies, and they do not require large cooling techniques, so we can save a lot of money in saving power as well as in maintaining the cooling system. Only thing we need to do is that we need power only to bring the material into superconducting state, and we need to maintain that material in the superconducting state so that it can generate high magnetic field, which we can use in research and medicine. So if we use superconducting materials to generate high magnetic fields, we are going to save lot of. So the development of superconductors has improved the field of MRI scanning, right? As a superconducting magnet can be smaller and more efficient than an equivalent conventional electromagnet. Okay, so because of the introduction or development of the superconducting materials, we are using the superconducting materials in MRI because they are small in size and more efficient than other materials. Okay, so that is the development of or using application of superconducting materials in medicine as which is in MRI scanning. Okay. So the fourth application of superconducting materials is that very fast electronic switches. We can use these superconductors in very fast electronic switches. Type 2 superconductors can be used as very fast electronic switches. We are going to use type 2 superconductors. Type 2 superconductors are going to change from superconducting state to normal state in a gradual manner, right? So type 2 superconductors can be used as very fast electronic switches due to the way in which a magnetic field can penetrate into the superconductors. So in type 2 superconductors, the magnetic field can not only penetrate the surface layer, but it can penetrate into the bulk. Okay, because of that, magnetic field generated by type 2 superconductor is high. Right. So this has allowed researchers to build a 4-bit computer microchip operating at about 500 times the speed of the current process, where heat output is currently a major problem with typical speeds approaching the 1 gigahertz mark. So type 2 superconductors can be used in fast electronic switches because of their because when you apply magnetic field, this magnetic field can enter into the bulk. Okay. So we can use these superconductors in making a 4-bit computer chip which is operating 500 times the speed of the process. It is operating 500 times more. Okay, so only problem is that there is a generation of heat. If we can maintain this high heat, then we can use these type 2 superconductors in making very fast electronic switches as well as in computer microchip operating systems. So the fifth application of superconductors is that cryotrons. The application of a magnetic field greater than its critical magnetic field changes the superconducting state of a superconducting material to normal state, and the removal of the field brings the material back from the normal state to the superconducting state. So we have studied that by applying magnetic field to this superconducting material, we can change the material from superconducting state to normal state, or by normal state to superconducting state below Tc or above Tc by changing this temperature. Okay, so even if the material is in superconducting state where T less than Tc, by applying magnetic field H greater than Hc, we can change, or this material can go from superconducting state to normal state for whenever the magnetic field is greater than the critical magnetic field. Or when we reduce the field below Hc, again the material will come from normal state to superconducting state. So this transition is reversible. By changing the magnetic field, we can go from superconducting state to normal state, or normal state to superconducting state. So this fact is used in developing cryotron switches. So that is the reason why we can go from superconducting state to normal state, or normal state to superconducting state by varying the magnetic field, applied magnetic field. So that is the reason why we can use these superconductors as cryotron switches. The sixth application of superconductors is the maglev trains. The most spectacular application would be the so-called maglev trains. Okay. So this is the most spectacular application of superconducting materials, right? So the coaches of the train do not slide over steel rails but float on a 4-inch air cushion above the track using superconducting magnets. So we have studied that one of the property of superconducting material is that it is going to act as a perfect diamagnetic material. So the property of a diamagnetic material is that it is going to repel the applied magnetic field. You apply magnetic field, this superconductor is going to repel the applied magnetic field. So if you can make this if you can make the coaches or the train with superconducting material, and you have 4-inch air cushion above the track using superconducting magnets. Okay, so then if this is a superconducting material, this superconductor is going to repel this, right? So that is why this will float in air. Okay, so this will float in air so these coaches of the train do not slide on steel rails but float on a 4-inch air cushion above the track using superconducting magnets. So this eliminates friction and energy loss as heat, allowing the train to reach high speeds of the order of 500 kilometers per hour. Okay. So the spectacular application of superconductor is maglev trains. So there is a levitation. So this, if you have superconducting material or superconducting track, okay, so this is a superconducting track, and you have a magnet. These coaches are made with magnet materials. Then these tracks are going to repel these tracks which are in superconducting state. Then they are going to repel these magnet. They are the cushions or these coaches made by these magnetic materials. Okay, so that is the reason why these train or coaches are going to float in air. This is why it's called as levitation. These coaches are going to levitate in or float in air. Okay, because of this diamagnetic property of a superconducting material. Diamagnetic property is nothing but this. When the material is in superconducting state, it is going to repel external magnetic fields. Okay, so because of this property of repelling external magnetic field, so these superconducting tracks are going to repel the train coaches made with magnetic materials. Okay, so that is why this train is going to float in air, and they are going to this train is going to travel with this speed of 500 kilometers per hour. So this is one of the spectacular application of superconducting material, and we can replace all these current trains by these superconducting or maglev trains only if we can manufacture the superconducting material that can work at room temperature. If we can manufacture a superconducting material which can work at room temperature, then we can use that superconducting materials in making up the tracks, and then we can have these maglev trains which are going to travel speed of 500 kilometers per hour. Such magnetic levitation trains would make train travel much faster, smoother, and more efficient due to the lack of friction between the tracks and train. Okay. So if we can prepare or if we can develop superconducting material that can retain its superconducting property at room temperature, then we will have these maglev trains. If we have maglev trains, they are going to travel very fast, around 500 kilometers per hour, and we are going to save lot of power, and such trains will be faster, smoother, and more efficient. So the last seventh application of superconductors is squids. Okay, what is the squid? Squid is a superconducting quantum interference device. SQUID. Superconducting quantum. QU is from quantum. I is from interference device. So a squid is a device used to measure extremely weak magnetic flux. Okay. So if we use superconducting material in making up squids, these are going to measure extremely weak magnetic flux. Basically, we can use that as a basically squid is nothing but a sensitive magnetometer. Okay, so because of this, this squid is a superconducting quantum interference device which measures extremely small magnetic flux. We are somehow generating magnetic flux or magnetic field, and it is very small, but we need to measure the magnetic field, such very weak magnetic field. Okay, so that can be done by this device called squid. Okay, which is a basically very sensitive magnetometer. Okay, so these are the some reference books which I have used in making up these presentations, and you can also look up all these books for more details. And to summarize, in this presentation, I have discussed in this presentation I have discussed about applications of superconducting materials, applications of superconductors, starting with power transmission, and then in electrical machines and transformers. We use these superconducting materials in transformers and electrical machines, as well as in power transmission. And the third one is in research, because superconducting materials can generate high magnetic fields. Wherever we need to generate high magnetic fields in research or medicine, we can use these superconducting materials to generate high magnetic fields. And the fourth one is in maglev trains, right? So fourth one is in very fast electronic switches, to make up fast electronic switches, because by changing the magnetic field, these material will go from change from superconducting state to normal state, from normal state to superconducting state by varying the magnetic field. So we can use this superconducting material as fast electronic switches. We can also use them in cryotrons, and we can also use them in maglev trains. If we can develop a material which will retain its superconducting state at room temperature, we can develop these magnetic levitation trains which are very fast, smoother, and very efficient. And the last one is that squids. Squid is nothing but a superconducting quantum interference device which will measure very small magnetic fields. So we can use these squids in finding out or measuring out the very small or weak magnetic fields. Okay, so in some superconducting materials, I have started with the first presentation. I have started with introduction to superconductivity, and also I have discussed the properties of superconductors. I have discussed about what is superconductivity and what is a superconductor, and then I also discussed about the properties of superconductors: zero resistance and critical temperature, critical magnetic fields, this diamagnetic property, which is also called as Meissner effect, right? So persistent current, so on and so forth. So that I have discussed in the first presentation on superconductors, and then I have this in the second presentation. I have discussed about classification of superconductors, and then I have discussed about VCS theory, and yeah, and then I have also discussed now about applications of superconductors. So I'm going to in the next presentation I am going to discuss about some numerical problems on superconductors. So with that I am going to close this module 4, and then we will start module 5, which is nanotechnology. So I'm closing here, and in the next presentation we will discuss about the numerical problems on superconducting materials. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.